everyone. Welcome to our very first lecture in our introductory chemistry class. So we're going to go ahead and cover just the information I kind of expect you to be familiar with, expect you to know from chapter 1. Again, this is where we're starting from square zero, and we're going to move forward from here throughout the semester. Every set of lecture slides that I post will look relatively similar to this. It'll say something about the chapter. I'll kind of try to give you an overview where I'm kind of putting the theme of the chapter into a couple of sentences or so, and then I'll have a list of learning objectives. I'll try to keep them specific to that specific set of slides. So some of the chapters later on might have a part 1, part 2, part 3 kind of a deal. So the learning objectives you see, you're responsible for all the learning objectives in those chapters, but you may see them broken up space by space in those different pieces of the slides and in the lectures. So we're going to go ahead, we're going to cover chapter 1 today. This is kind of just a little bit of a historical context, a little bit of information about, investigation and experimentation, kind of the scientific method is the deal here. And so by the end of this chapter, you should be able to define chemistry in your own words, establish a scientific thinking mindset. So how can we get our chemistry caps on? What can we do to think that one through? We'll learn a little bit again about that scientific method. So we'll identify the steps that we need to take to scientifically kind of prove something, if you can ever really consider that we've proved anything. Ooh, conspiracy theories. I'm just kidding. I'll get there. It's right until it's proven wrong, because throughout history we've had lots of different interpretations of science. And we'll also learn how to identify a few patterns and strategies when we're interpreting graphs. And we'll talk just a little bit about chemicals and atoms and things like that too, getting into the nitty-gritty of actual chemistry rather than a broader spectrum of science. So let's get into it. So what is chemistry? You signed up for my class. Hopefully you read the course description. You know why you're here. But just to put it in a more definition tone, chemistry is a science that seeks to understand what makes up the world around us. Why do things exist the way they do? Kind of investigating the makeup of the things around us. So, physics is going to study how maybe things move, for example. Biology is going to study living organisms. We're here to really go down to this teeny tiny level where we can figure out exactly what kind of things make up us and the rest of the world and everything we see around us, the universe, all the galaxies, maybe multiple universes. Who knows? We have no idea. Just kind of, that's really what we're trying to get into the nitty-gritty of, is studying those atoms and elements that really make everything up. But we'll get into a few more definitions about atoms and elements later. So this is going to look at all scales of the universe. So the electrons, protons, and neutrons, we'll talk about them. Those are the things that actually make up atoms. And then atoms hooked together, we kind of consider those to be the basic building blocks of the universe. Atoms, those hooked together, they make molecules. And then molecules kind of interact with each other to become that larger scale world we see around us. So we'll go all the way deep diving to what makes up an atom, all the way back out to how we experience them in our everyday lives. So we want to know how we can investigate, we can manipulate these materials. So by the end of the semester, we'll know why a hydrangea is blue or that pinkish purple tone. And so we could honestly change the color of that flower if we wanted to. And we'll kind of learn how to manipulate and investigate how we could manipulate those things. Again, manipulation meaning something like a chemical reaction when we mix stuff together and do some sort of change to what we're doing. So a more formal definition of chemistry is it's the science that tries to understand how matter, the stuff that makes everything up around us, how that behaves by studying how atoms and molecules behave. So we want to look at how things are happening on a very teeny tiny scale and broaden that up to see how that's going to affect things on a larger scale, or maybe we're kind of something's happening here, so I'll drill down. I'll figure out what's happening in this reaction. Then I can start to think about what's happening with those individual pieces that make everything up. So that's a little bit about what chemistry is and what we study. So let's talk about how to think like a chemist. Like I said, we got to put our chemistry caps on. So chemistry kind of comes with a very natural curiosity and inquisitive nature. Chemistry is really based off people just kind of being like, why do things happen the way that they are? And how can I make the things that I want to have happen? So we're constantly looking at the world around us. Why does it happen? How can I study it? So it's not only just looking around and saying, the sky is blue. It's why is the sky is blue? Why we want to know that. And we want to really get into the why of things. So a lot of times we'll be spending a lot of time in class truly working on making sure we understand the reasoning and the logic, and that's a real chemistry thinking mindset. So when you put your chemistry cap on, you want to know why. So I mentioned this in the introductory video. In that very first lecture I kind of gave, you have to really open your mind to new ideas and concepts, and it might take a few times. Chemistry is honestly a lot of hard work and persistence where, there are things that I think intuitively should happen one way when I see them happening, but really when you get down to that small scale level, that's not what's happening at all. You know what I mean? So it takes hard work, it takes persistence, and chemistry truly is a commitment. It's a commitment to wanting to understand why and continuing to persist through when you don't totally understand so that you can really get down to the nitty-gritty and figure out which piece it is you're missing so you can bring that whole picture together for some level of understanding. So chemists also really like to look for patterns in relationships. So if we do a reaction and we do it 20 times, and the same thing keeps happening, we're looking for that pattern. We want to know what's happening, and we want to reconfirm that things are happening the way that they are. Or we want to see what happens when we're creating new relationships between things. Maybe we haven't seen two things mixed together before, so we want to know what happens. And we're going to look for a pattern when we start to mix different things together as well, for example. This is, again, just broad examples. So really, when you learn to think like a chemist, you kind of unlock a new way of understanding how the world works around you. So realistically, a lot of times I am thinking about how things are mixed together. I'm thinking about, the desk, even though I'm touching this desk in front of me, I'm not really touching it. And we'll get to what I mean by that by the end of the semester. But my friends will often pose questions while we're talking about stuff, and I'll be like, I bet I could come up with an answer for that. I can put my chemistry cap on, and I kind of got something to think about there. So anyone can be a chemist. Anyone can learn chemistry if they put their mind to it. So please, again, when we're in chemistry class, we're putting our chemistry caps on. We're letting go of that negativity that chemistry is hard, and we're going to work to set our mind into these kind of things about how to think like a chemist. Okay, so scientists everywhere tend to use the scientific method. It is a way for us to kind of follow some rigorous steps so that we can prove a little bit more strongly that we've kind of covered all our bases. So my theory seems pretty reasonable. That doesn't mean things can't go back and be changed. However, this kind of gives us a basis to work from where we can think that we've at least confirmed something for now. So the first step to the scientific method is observation. So this is taking measurements about the world around you on lots of different scales. Again, this can be used by any kind of scientist. So, that may be physicists and astronomers studying galaxies, or it may be chemists and like quantum physicists studying things at little teeny tiny levels. Biologists studying big animals or cells. It can be at any level. So this would be that portion earlier when I said, yeah, you notice that the sky is blue. The rest of the scientific method is for you to prove to yourself why. So an observation may be intentional or unintentional. So I've got a couple of examples we'll work through here. We'll talk about Lavoisier throughout the semester. So you'll hear his name again. He'll be back, I promise. But I feel like there's a good Terminator reference there. I'll be back. So anyways, if we're thinking about intentional observations, there's a French chemist named Lavoisier, And so he was studying combustion. So he wanted to answer some questions about combustion. What happens when you light something on fire? So he did lots of experiments where he was able to have something combust while it was sealed in a jar, so he knew nothing was coming in or out. And he wanted to know what happened when you did that. So he was intentionally doing experiments to help him understand the world around him, and what he wanted to understand was combustion or fire. An example of an unintentional observation would be the scientist Fleming. He was studying bacteria in a lab, and he left for the weekend, came back on Monday, and he noticed in one of his petri dishes where he expected to have been growing bacteria that there was some weird mold growing in there instead, and no bacteria? What? So he was confused. He wanted to know what was going on, and it was unintentional that this happened. To be honest, they think it was mold coming from another lab that literally went through like the ventilation system and barely happened to land on that petri dish, which had one of the biggest medical breakthroughs. Life is, unintentional consequences, let me tell you. But he discovered penicillin by doing that. That mold that was growing was penicillin. Yeah, penicillin's mold, kind of gross. But it's been life-changing for humans that we can now help treat bacterial infections and things like that using this mold that he accidentally found in his lab. But it's still an observation, no matter if it's an unintentional thing that has happened. Okay, so once you have those observations in place, the next thing you have to do is do some sort of interpretation. You need to do something about that why question we were talking about earlier as a scientist. So once you have that observation, we tend to therefore make what we call a hypothesis. So this is some sort of interpretation or explanation of the observations. It's tentative until we have a little bit more information about what's going on to kind of say, I can still say my hypothesis holds true, or the data shows it ain't happening. So a good hypothesis is what we call falsifiable, so it can be proven false. So all the time scientists are literally collecting data to try to prove something wrong rather than trying to continually build up the information we kind of already have. If something's working the way it is, kind of to continue to prove it right, we tend to try to prove things wrong, and we're like trying to find better methods or better ways. An example from what we were talking about earlier with Lavoisier studying combustion, what he did was he formed a hypothesis. So when he was doing his reactions, he would take the mass, so he would take, we could consider it the weight for right now, so he'd take the weight of the jar, he'd do the reaction, he'd start with one thing, do the reaction, end up with something else. You light something on fire, you end up with something different. And he'd take the mass at the end. And so he was trying to figure out what was going on, because when you had that weight at the beginning and you had the weight after the reaction, it was the same weight, even though it was something different that you started with. So he was trying to figure this out, so he came up with a hypothesis that, the mass isn't changing. There's air sealed in that jar. When he screwed the lid on, made it airtight, there's still air in there. And so when that substance is changing, that mass isn't going anywhere. That amount of matter, that stuff that's in the jar, isn't going anywhere in a sealed jar. So when we're doing chemical reactions, I guess I have the same amount of stuff before and the same amount of stuff after. That was what he kind of came up with as a hypothesis. So he again continued to conduct experiments to try to prove this hypothesis wrong. What could he do to change this, to say it's wrong? So experiments are considered highly controlled observations. So once Fleming discovered that penicillin unintentionally, he was going to do lots of testing with it to see what was going on. He was going to perform lots of experiments, even if it was an unintentional observation. The experimental piece of this is very, very highly controlled, very down to the nitty-gritty, as controlled as we need it to be. So we're trying to either confirm the hypothesis and say, hey, I can't find any data that proves this wrong, or again, we're trying to go with that falsifiable step and continue to try to prove it wrong. So we're either trying to prove it wrong or say, hey, I haven't found anything that's proved this wrong just yet. So a hypothesis can be modified and updated if they're proven inaccurate in some capacity. So Lavoisier kept measuring the mass, lighting stuff on fire, measuring the mass again. Kept doing it and doing it and doing it in all these closed containers because he wanted to know what was going on. And so he did this repetition over and over again to try to prove his hypothesis wrong, that, the mass is the same before and that mass is the same after. So once you are able to kind of settle on what's going on, you might make something called a law. So this is a statement that uses past observations to predict future ones. So you're kind of saying, hey, this has happened all the time doing this one thing. I bet it happens every time you do something similar. So it's subject to experimentation for validation. We don't just call something scientific law and say, boom, done. That's it. Case closed. I'm out. You know what I mean? We're going to continue to experiment for validation to, again, try to prove wrong. And so what Lavoisier did was he thought of the law of conservation of mass. So the law of conservation of mass says that before a chemical reaction, we have a certain amount of mass, and afterwards, we'll have the same amount of mass. Mass is neither gained nor lost in a chemical reaction. So that's what he came up with, and we call that the law of conservation of mass, because I can predict that in every chemical reaction I do, this law will hold true. And nobody's found any data to prove this false. So that is the law of conservation of mass. So once we've kind of settled on something and we've proven that hypothesis, we can't prove it wrong, we can settle it into kind of a scientific law. Another thing you might end up settling on is a theory. So this is much broader than a law. It's a bit more of a model about how nature truly works. So you kind of go beyond those observations and beyond the law that it might come from. So they're still subject to experimentation, but it's kind of a broader thing, maybe bringing together lots of different observations from different areas. So the book talks a little bit about Dalton and his atomic theory. So when we're talking about atomic theory, we are bringing in observations and laws and ideas and thoughts from lots of different areas, and we're really trying to get down to the nitty-gritty about how nature works. Whereas the law of conservation of mass applies to chemical reactions, Dalton and his atomic theory applies to basically everything, and we can use it to predict lots of different things. We could use it to predict the size of an atom. We could use it to predict how an atom might interact with another atom, and on from there. So it can be applied in many different ways, because it's a model truly discussing how nature works. So, as I've been mentioning, this is all subject to revision. We could continue to try to prove something false, and eventually we might. For how long did human beings think that the Earth was the center of the solar system, right? We thought that everything in the galaxy, everything in space, everything around us, all of those heavenly bodies, we thought that the Earth was the center of all of that. And that stayed for a long time. Nobody had any information or data to prove it false. And then, in the end, we did figure out that we live in a heliocentric system. So the sun sits in the center of the system, and we are all traveling around at Lord knows how fast around the sun at all times, and then that makes the solar system. Then there are lots of solar systems that come together to make a galaxy and a universe, and now we have all of this bigger information and a broader view of the way space works. So everything can be revised. Just because we think we know it now, it just means we haven't been able to prove it false just yet. So all hypotheses, all experiments, all laws, all theories are always being maybe partially revised or entirely revised based on new evidence gained through new experimentation and observation. So this is what everyone's slaving away in the lab doing science about. We're really trying to make a new observation, push science further, trying to gain new understanding, or maybe even prove something false, right? So this is truly the most important part of science, that we're always hungry, we're not content. We want to continue to improve and move science forward and keep going on and on and on. And we can't do that if we say, it's a law, I'm done. Boom, end of discussion. But it doesn't work that way. And if we continued to do that, we'd still be thinking the Earth was the center of the solar system, and that would be where we were. So You got to make sure we're revising, and there are lots of brilliant people in the world studying this all the time. And, you know, when we put our chemistry thinking caps on, you guys are those brilliant people helping to collect that data and help that understanding. So that's the scientific method. So you should be able to really interpret this, understand it, have a good idea of what's going on, and that nothing is ever really set. When scientists are kind of using the scientific method, we're collecting all of this data in our experimentation step. What we tend to try to do, and what scientists love, chemists love especially, is identifying patterns within that data. So data is just a set of measurements gathered through observation and experimentation. So for example, the record of the highest daily temperature every day for the year 2020 in Moline. That's a set of data. I can get all of those temperatures and I can do some stuff with them, try to figure out what's going on, compare them, compare 2020 to 2019 and other years in the past. Or you might think about, you know, one thing we talk about, I don't know if you guys talk about it quite often, but I tend to talk about these things. But you might think about, you know, when they're first testing cars, they're going to see how fast it goes 0 to 60 miles per hour. So you might know this about a bunch of different cars. So that's a metric that you could take where you have this set of data about lots of cars where you can start to compare the cars in different ways. So you could pause the video, kind of think about, you know, what are sets of data that you interact with in your daily life. I check the weather all the time. That's my main set of data I interact with. But, you know, I know that when I conduct experiments, I'm going to end up repeating them and coming up with lots of different sets of data. So I probably interact with that a lot too. What I want you guys to do is kind of take a look at this. You can either pause the video here, check it out on your video screen, pull these slides up separately from where I've posted them on Canvas in the module. And what I want you to do is see if you can't compare these numbers and see if you can't find some sort of pattern in this data. It's really, really good to pause here and practice for yourself before we move on. So go ahead, pause, check it out, see if you can't figure out how the numbers on your screen here are related. So what does this mean? What am I showing you? Well, this is an example of the law of conservation of mass. So we'll talk a little bit more about this in a second, but water is made up of 2 hydrogen atoms and 1 oxygen atom. That's what we're saying when we say H2O, right? We've heard H2O before. So 2H, like H2, 2H, 2 H's, 2 hydrogens, and then you just have 1 oxygen hanging out there as your O. So when you split water into its components, so when you split it into hydrogen and you split it into oxygen, it should have the same total mass. So if I start out with 20 grams of, if I start out with 20 grams of water, the mass of hydrogen that I get, so the amount of hydrogen I have, should be added to the mass of oxygen that I get, and that'll equal my 20 grams. So 2.2 is plus 17.8 is 20. 50 grams, if we break that into the hydrogen and oxygen as well, you get 5.6 plus 44.4, which again adds back up to that 50, and so on and so forth. So that is one piece of data that you could interpret from this, or it's one pattern you can find in this data. But that was kind of the fun connection here, is that this is the law that Lavoisier came up with. So we have an example here of data that helps confirm the law of conservation of mass. And so we might be able to interpret the same data in many different ways. So when I just talked to you right there, what we did was we added those last 2 columns, and it gave us the value in the first column. However, there are many things we can learn from one experiment. So we can also see that if we take the ratio, so we take the mass of oxygen and we divide by the mass of hydrogen, we get almost the same answer every time. This is pretty dang close. So we have this ratio that keeps popping up if we compare these numbers to each other, through division rather than adding them. So there are many different techniques you can take when you're in identifying patterns in data, when you're trying to interpret what's going on. So it's really good to keep an open mind. And, maybe when you pause the video and you were kind of doing some scratch work yourself, you came up with something different than the two interpretations I've shown you as well. So keep that in mind, that there are lots of different things that you can learn from just one experiment. And, in graduate school, we'd maybe publish 2 or 3 papers that had to do with the same set of data because there were lots of interesting things happen that could be interpreted many different ways. So the other thing that we might often do in class is interpret graphs. So one thing you can do with a set of data is plot it on some set of axes, right? So graphs are just visualizations of the data. They help you with interpretation. So here we have a graph that represents the amount of atmospheric, so up in the air, how much carbon dioxide is there. So it's a graph that represents atmospheric carbon dioxide. When we're looking at this graph, I want you to be able to look at graphs and kind of answer questions like these ones here you see on your screen. I'm going to kind of talk through the questions, but before I do that, see if you can pause, figure this out on your own as well. So you could pause in between each of my pieces of conversation about this. And you can find all these answers in your textbook as well. If I wanted to know what the concentration of carbon dioxide is in 1960, I can see that here I have the years labeled in about, it looks like 40-year gaps with a little dash in between. So I can count these as 20 years each. So I would think this is 1860, 1880, 1900, 1920, 1940, boop, 1960. So if I want to know what the concentration of carbon dioxide was, how much carbon dioxide was there, I would just follow up that 1960 line and see where it intersects our data line. So this is all of the data plotted in the red, and you'd go all the way up here to say, boop, at 1960, I'd say that's a little less than 320 parts per million of carbon dioxide, for example. And then we could compare that to what happened in 2000. So if this is 1960 and 1980, and then this must be 2000. So in 2000, we can see that it's much closer to 370. That would be the dash here. You can see that these go by tens. And that would be 370 parts per million. So we can compare those two values, saying like how much did the concentration increase. And we can estimate and kind of carry our graph out further. If we see this rate of change happening, we see how quickly we're increasing the amount of carbon dioxide in the atmosphere. You can kind of start to predict even further on your graph. So go ahead and make sure you're checking out all of these answers you can see in your textbook as well. Kind of getting into a little bit about what we mean by chemicals, what we mean in chemistry. I've been using words like atoms and molecules and things like that. Let's talk just a little bit about it. That way I can start using these words for the rest of the semester with you. So chemicals compose ordinary things. Everything around you is a chemical. I'll tell you that right now. I'm sure you can't give me an example right now where I wouldn't consider that to be a chemical. So we often hear at the grocery store, oh my God, on commercials, this drives me nuts. My parents are sick of me saying, that's not real, every time I hear this on a commercial, let me tell you. But we often hear things like, no added chemicals, chemical free, when we're thinking about maybe like cleaning products or something. What does that even mean? What does it mean? It means nothing. It literally means nothing because everything's a chemical. So if you made something, you added chemicals. If you have a literal substance with you, it's a chemical, so it can't be chemical free. Oh my God. It cracks me up every time I see it. My parents have been like, you gotta stop. You gotta let them go. It's not the way it works. So chemicals make up everything around us. Everything you can touch, feel, see, look around, interpret, do, move, whatever, chemicals. So atoms are chemicals. And they're the building blocks of the universe. So we consider them to kind of be the smallest unit where we can identifiably tell them apart. We can see what these different things are. They're made up of smaller particles, but those particles could be anything, whereas an atom has a specific identity. So we consider that to be like the smallest building blocks of the universe. So you, your dog, your car, your house, the table you're sitting at, the most pure water you could drink, the sun, the Mississippi River, the coffee you have every morning to stay alive. Let me tell you, I have that coffee every morning to stay alive. Those are all chemicals. Your literal DNA that makes you as a human being happen is a chemical. Everything around you is chemicals. So if you can feel it, you can see it, you can touch it, you can smell it, you can observe it, you can make a really good argument that it's a chemical. There are a few technicalities, we'll talk about it, but everything you see around you is a chemical by definition. So I keep talking about these little small particles. What do I mean by that? Well, atoms are tiny particles. The smallest unit that really makes up identifiable matter is what we're talking about. Well, again, there's a star there. There's a little caveat. We'll talk a little bit about that. However, my intent here is that it's an identifiable unit. It's definable. You can tell it apart from something else. So that you can see what it is, and we'll, again, talk about what makes up atoms, but let's get that out of our minds. Atoms are the smallest particles that are out there. You can kind of think of them like a Lego, okay? So they come in different colors, different sizes, different shapes. They have different purposes and properties that can be characterized by these traits. So, you know, you might have like those flat green bricks that always remind me of grass, where you're going to build bricks on top of them, but you have those individual Lego bricks that are a little bit different, right? So the ones with like 6 pegs, 8 pegs. You know, I built a spaceship, like a space shuttle Lego set over the summer. I know, I'm real cool. But I built that, and so it took a lot of different parts to come together to make that Lego spaceship. So there were lots of different kinds of Legos to do that. So therefore, like, those kind of represent our atoms. However, molecules are atoms that are stuck together to form a bigger structure. So these are like the things you can build from your Lego. So that's like my spaceship. I've got a TIE fighter at home I'm going to make. I have built a Republic tank and stuff like that. So there's lots of different things you can build from your Lego. And I could take all of those apart, take all of my Lego, and build something crazy out of all of these different things together. So it could be simple. It could be just, again, you know, maybe 2 Lego stuck together, or it could be really complex, like some of the things I've mentioned that I've built. They come together to really make what you see with your eyes. We're not looking around and like zooming in with our own eyes and seeing individual atoms. What we're seeing is what molecules have come together to make these bigger things that we experience in the universe. So a molecule might be like that space shuttle I put together, for example, with my Lego. So I might have those individual Legos, they stick together, they come together, and now I've got a space shuttle. So that's kind of an interpretation of atoms and molecules. And throughout the semester, what we're going to start with is talking about the atom in very fine detail. Then we'll talk about, in the second unit, how atoms come together to make those molecules and kind of form those bigger things and make chemical reactions happen when they do that, and so on and so forth. So we'll talk more about these. These are very broad, just kind of explanations so that we can continue to use words like atoms and molecules. So, for example, here, we talked a little bit about this earlier, but this is a water molecule. So this is what we call a space-filling model. We'll talk a little bit more about all the different ways we can model atoms in the future. But this red chunk right here in the middle, that's representing the oxygen atom, and it has 2 hydrogen atoms on either side. So this is one whole water molecule, but it's got 3 atoms in it. So it's got 1 oxygen atom, 2 hydrogen atoms, and then they come together to make this bent shape for reasons we'll discuss soon. But they come together to make this bent shape of a molecule. So once atoms come together, things kind of change a bit. It's a little bit different. We can see that when we add those atoms together, molecules are maybe going to behave a little bit differently than those individual atoms might have. And so we've got 3 atoms making up 1 molecule here. So those are just kind of some definitional terms. Here's a more visual version of what I mean by atoms and molecules. So what I want you to remember is that everything around you is made of atoms that are bonded together to form molecules. Those molecules interact with each other to create the world we interact with on this big, broad scale that then makes the solar system, makes the galaxies that make the universe. Atoms make up everything, even those teeny tiny particles that then go out and make something as large as the universe. It all comes down to atoms. So the next time you hear chemical free at the store, be very skeptical, please. I'm begging you. Think twice when someone's trying to gimmick you into buying something saying it's chemical free. All right, so that's our information here for chapter 1. Again, go back to those learning objectives there on the first slide so that you can make sure that you've kind of gotten everything you need to get out of this lecture. Maybe you need to go back, brush up on a few parts, but that's chapter 1.